Good day, everyone. How are you? I welcome you back to my YouTube channel. And by God's grace, today in our video lesson, we want to explain in detail the concept of simple harmonic motion. Simple harmonic motion. And in this video, we will try as much as possible to learn the definition of simple harmonic motion. Then after that, we look at examples of simple harmonic motion. So we would explain and give examples of substance or systems that undergo simple harmonic motion. Then similarly, we would explain some terms that are used in describing simple harmonic motion with vital equations for each case. We will look at that. Then also we will explain energy change in simple harmonic motion, and there we would derive the equation for calculating instantaneous velocity. Then also in that concept, in this topic, under the topic, we would also explain resonance in simple harmonic motion. Then after explaining resonance, we make sure to explain the concept of damping. So we would explain the concept of damping. So I repeat, we gave the definition, explain examples, we describe the terms used in describing simple harmonic motion, and together with the vital equations, formulas. Then also we explain energy change in simple harmonic motion. When I say SHM, it means simple harmonic motion. Then also we explain instantaneous velocity, then resonance, then damping. So now we're starting with the first thing on the agenda there, which is the definition of simple harmonic motion. So how do we define simple harmonic motion? Now, simple harmonic motion is actually defined as the to and fro motion of an object. Okay, so the to and fro motion where acceleration of a body is proportional to displacement and directed to the center of motion. Okay, so and directed to the center of motion. We said simple harmonic motion is the to and fro motion where acceleration of a body is proportional to displacement and directed toward the center of motion. Now, what does that mean? It means that, writing equation, acceleration varies directly as displacement. That is the first equation we're going to write. Now you see minus x here, meaning the acceleration varies directly as minus x. Now what does this minus in this equation indicate? It simply means that acceleration and displacement are not in phase in simple harmonic motion. They are not the same. So meaning acceleration and displacement are actually out of phase with respect to simple harmonic motion. So any motion undergoing, any object or system undergoing simple harmonic motion, we have two things that are out of phase. Acceleration and displacement are never the same. They are never in the same projection. So acceleration is out of phase with displacement. So that is what this minus sign here indicates. So you can pause the video and then rewind, then you listen again. Okay, that is the meaning of the minus sign as it is there. Now we want to, by God's grace, look at examples of body or bodies or system undergoing SHM. Example of bodies or system undergoing SHM. So now the first example is an oscillating an oscillating simple pendulum, okay, in vertical plane. All right, an oscillating simple pendulum. So you will see that, okay, as you can see that in the diagram. So that is an example of oscillating simple pendulum in the vertical plane. Then another example of a system undergoing SHM. Another example of a system undergoing SHM is a loaded test tube oscillating in a liquid. When you place a loaded test tube that is loaded, and then you place it in a beaker, okay, you place it in a beaker containing liquid, so the test tube will actually be oscillating. So that shows that it's also undergoing simple harmonic motion. So that is another example. We got a loaded test tube. Then the next one is a diving board when used by a diver, okay, as you can see. So immediately the diver leaves the diving board and venture into the water, then you see the diving board going up and down, to and fro. So that also shows another example of simple harmonic motion. So another example of a system which undergoes simple harmonic motion is the motion of the wheel of a wristwatch. The motion of the wheel of a wristwatch also exhibits simple harmonic motion. So those are examples of system undergoing simple harmonic motion. So now we move to the next thing, which is terms used in describing simple harmonic motion. So we got terminologies. There are some terms that are employed, that are used when explaining simple harmonic motion. Now, what are those terms? What are the terminologies that are employed when explaining the concept that has to do with simple harmonic motion? So now, the first one is amplitude. What is the meaning of amplitude? So amplitude is the maximum displacement from the equilibrium position. The maximum displacement of an object when the object go to and fro. So the highest point it can reach, okay, vertically, is what we refer to as the amplitude. So it is the maximum displacement from the equilibrium position, from the center. And the maximum, the best way, the best end it can actually reach is the maximum. Now let's assume this is so that is a bulb. The vertical, that is please. Now this is a simple pendulum, and you have the bulb. Now this particular point here where the object can reach, okay, this particular end, that will be its maximum displacement, okay, not when it is at this side, but rather the edge, the edge. So that is the first terminology So we have amplitude, which is also known as the maximum displacement. Now we have the second terminology, which is equilibrium position. So how do we define that? So equilibrium position is actually the point where the body has its highest velocity. Okay, the point where the body has or experience the highest velocity and greatest kinetic energy. That is the meaning of equilibrium position. Now, where do we see that? Let's see. Let me draw this diagram of a simple pendulum oscillating to and fro. Is oscillating to and fro. So I drew the other time to show us the maximum displacement. Here the object has the maximum displacement. So it went to, and then it can also go through the other side. Okay, to this side, this is the maximum displacement. To this side, this is the maximum displacement. So now the question is, where will be the fastest, or where is the equilibrium position? This particular point here is the equilibrium position. That is where the object will actually have the maximum velocity. This particular point here, the object will have the maximum velocity, and there it will experience the greatest kinetic energy. Not this side or this side, but rather this center, this middle part. So equilibrium position is the point where the body has the highest velocity and greatest kinetic energy. So please do well to note that. So that is the second terminology we use in describing simple harmonic motion. Now the third terminology is displacement, and that is defined as the distance covered horizontally. The distance covered horizontally from the equilibrium position. Okay, the distance covered horizontally from the equilibrium position is known as the horizontal displacement. Okay, it is actually expressed as, so what is the equation for equilibrium position? Okay, as we can see here, the equilibrium position, horizontal displacement, that has the symbol x, is equal to a cos omega t. So that would be the second equation. This x here is the horizontal displacement. A is amplitude in meters or millimeter. Then we have cos. Omega stands for the angular frequency or angular displacement in rad per seconds, radian per seconds. Yt stands for time in seconds. So excuse me, please do well to note that. Okay, now the next terminology we use in describing simple harmonic motion is velocity. Velocity is another terminology used in describing simple harmonic motion, which is defined as the rate of change of displacement. It is defined as the rate of change of displacement. Okay, so how do we express that? So we can say that velocity is equal to change in x divided by change in time, that is the x over the t. But from the above, we knew that x is equal to a cos omega t. So we can substitute our x, which is equal to this, in this equation. Now this equation is very relevant, equation 3. So when we substitute x in that, so we have that velocity is equal to d. Instead of writing x, we write a cos omega t. A cos omega t. Then you bring down the t. Now we can bring this a out so that we can differentiate this. So we rewrite that by saying that velocity is equal to a d cos omega t over the t. So we can now differentiate cos omega t. Now when we differentiate cos theta, mathematics, we have minus sine theta. When we differentiate cos theta, we have minus sine theta. So now, when we now differentiate cos omega t, so what we will have is velocity equals minus a, okay, omega sine omega t. All right. So which means that when we differentiate this cos omega t with respect to t, we have minus a omega sine omega t. Now that we use to calculate velocity, and that will make it the fourth equation number 4. Okay. Now, but meanwhile, for maximum velocity, okay, for maximum velocity, or when velocity is maximum, sine omega t will be equal to 1, will be unity. So therefore, we have that velocity is equal to, at this maximum velocity rather, will therefore be equal to minus omega t. All of this has been changed to 1, and 1 multiplied by this will give you this. So this equation is also very relevant. So you can pause your video, digest this so that you can know this, so that you can assimilate better. So that is the equation to calculate the maximum velocity. That is the negative values of amplitude multiplied by the angular frequency. Okay. So now we quickly proceed to the next terminology. Terminology is, so what is the next? Acceleration. And what is acceleration? Is the rate of change of velocity. Okay, so that is acceleration, and which means a is equal to change in velocity divided by change in time. So we're going to differentiate that now, but we learned that velocity, okay, is equal to minus omega, okay, we substitute the value for velocity, that is d minus a omega sine omega t. all over the t. Okay, so when we bring these two out, you bring them as a constant so that we can differentiate this. So that acceleration will be equal to minus a omega d sine omega t dt. Okay, so we cannot differentiate this. Minus sine theta is cos theta. So now when we differentiate this, acceleration will therefore be equal to, this one will give us minus omega t will be cos, omega t. So now on differentiating this, we have minus a omega cos omega t. So when we differentiate this, we got this. So omega multiplied by omega, that is the angular frequency, that will be minus a omega squared. Okay, when you multiply this and this, cos omega t. All right. So now when we rearrange this equation, we can have, simply on rearranging this, we have that a equals minus omega square a cos omega t. All right, so we can use this to unravel and get a value for acceleration, and that will make it equation 5 if I'm not wrong. But we learned that horizontal displacement is equal to a cos omega t. So we can substitute this in this equation, a cos omega t, and that will now give us our acceleration, okay, to be equal to, so acceleration will be equal to minus omega square. So instead of writing a cos omega t, you substitute this here, then x. All right, so that also we can use to get our acceleration when it has to do with simple harmonic motion. And the maximum the maximum acceleration can also be calculated by saying minus omega square multiplied by amplitude. Okay, that is when the body will experience the maximum acceleration, when it is at the terminal displacement, like we have in this diagram here. So we have the maximum acceleration at that point. Now, the next terminology we use in describing simple harmonic motion is period, and it is actually the time taken to make a complete oscillation. Period is the time taken to make a complete oscillation, which means that period is equal to time divided by number of oscillation. Okay, and the symbol for period is T, capital T, is equal to small t divided by n. Okay, so that's another term. So another term we use is frequency. And what does it mean? What is the meaning of frequency? Is the number of complete oscillation made per seconds. Okay, the number of complete oscillation made per seconds is the frequency. So as a result, we have that frequency F is equal to number of oscillation or number of complete cycle divided by the time taken. That is frequency rather is equal to N over T. So we can see that frequency is just the opposite, the reciprocal of period. Frequency is actually the reciprocal of energy changes in simple harmonic motion. Energy changes in simple harmonic motion. Now look at the bulb of a simple pendulum displaced horizontally as shown in this diagram. So the bulb actually displaced vertically, and we have different points. We assume this point here is point A, this is point B, and this is point O. Alright, so now the body tends to move to and then fro, and as a result, at this particular at point A and B, there is displacement, and the body tends to have gain potential energy here. The object is meant to be very fast and has the fastest velocity at point O, because the energy here is entirely kinetic. So as we move to B, kinetic energy is actually conserved and being transformed to potential energy. Then coming back to A, then goes to, coming back to O, then back to A. So now at point A, it also experiences the greatest potential energy. Okay, then on coming back to O, it has kinetic energy. Kinetic energy become maximum, and kinetic energy start decreasing and then changes to potential energy, then changes again to kinetic, then decreased to become potential energy. So which means that if the total energy of this system is 100 joules, for instance, now the addition of the kinetic energy and the potential energy, okay, will be equal to the total energy change in the system. So energy is not lost. So the initial potential energy plus the kinetic energy is equal to the total energy change in a system. So which means that the 100 joules of energy is not lost. So this is potential energy, this is kinetic energy. And we know that in an elastic material undergoing SHM, okay, the potential energy is half K x squared plus half mv squared, which is the kinetic energy, okay. So the total energy is equal to half Ka squared. Now when we multiply all through, by 2. We multiply this equation all through by 2. So we have 2 multiplied by this. When we multiply 2 by this, so 2 we cancel 1 over 2. So we have KS squared plus MV squared equal to KA squared. Alright, so we have the K's. Let's bring the K's together. There is a K here, there is a K here. So that our MV squared will be equal to KA squared minus, this is coming to this side, KS squared. So MV squared is equal to, on factorizing this, we have K is common into the bracket of A squared minus S squared. Okay, so on dividing both sides by M, we have that V squared is equal to K over M into the bracket of A squared minus S squared. So now on square rooting both sides, so square root we everly cancel square, so that your V will be equal to the square root of K over M multiplied by A squared minus S squared. Alright, so that is a velocity. Now when we rearrange and we calculate this, we separate in with the knowledge of sort these values. We have A squared minus then S squared, separate. So this can also solve a problem to separate this. Now, but you need to know the angular frequency is equal to the square root of K over M. Okay, so we can now substitute that in this equation. So we have that velocity is equal to angular frequency, okay, multiplied by A squared minus S squared. This equation is very, very important when it has to do with simple harmonic motion. Alright, so V here is actually the instantaneous velocity, okay, in meter per seconds. Omega is the angular frequency or angular velocity in meters. A is the in rad per seconds. A is the amplitude in meters, and X is displacement, okay, also in meters. So now I want you to learn this very well. This equation can also be used to solve question in SHM. Now the energy is actually conserved in simple harmonic motion, and energy is not lost in any context. So we see the conversion of energy from kinetic to potential energy, then from gravitational potential to kinetic, back to kinetic, and then to gravitational potential, because that height has been attained. So we've seen equation giving us the expression for instantaneous velocity for a system undergoing SHM, simple harmonic motion. Now quick one we explain as well is the next thing to explain is the resonance in SHM. So what is resonance? Okay, resonance is a phenomenon, okay, where an oscillating object or body sets another body, all right, into oscillation with its own fundamental frequency. A body that sets another body into oscillation and itself having its own fundamental frequency. So meaning at equilibrium, for equilibrium to occur, for us to have resonance rather, there must be, for a body to set one another into oscillation, okay, for a body to set another body into oscillation, they must actually be in phase. Like you can see in this video, the man is using different sets, trying different frequency, but the situation where the frequency are the same, then you can see what actually happened. Okay, so that could be illustrated on paper as well, where we have different bodies. Sorry, my screen drags. So this is a pendulum. This is another pendulum. Here we have another pendulum. So if this is A, B, and C, for instance, so A and C will be in, A can set C to oscillation because they are in phase, so they will exhibit resonance, but not with B. B is not in phase with them. Now we have finally damping. And when does damping occur, or what is meant by the word damping? It actually occurs as a result of air resistance. Okay, it occurs as a result of air resistance. So that is, so it is actually due to decrease. It is due to decrease in the amplitude of a body. It is due to decrease in the amplitude of a body. So we have here that it leads to decrease in the amplitude of a body. Okay, when the body eventually, come to rest, when the body is eventually brought to rest. So we can actually explain that, as we can see here in the diagram, an object that is properly undergoing SHM initially and was eventually, due to circumstance, maybe there is no air, it was brought to rest. So that is brief diagram for damping. Alright, so that is damping. So we stop here.